Hello everyone. We continue with Chapter 5, Trigonometric Functions and Equations, specifically Section 5.3, Graphs of Trigonometric Functions. First of all, we're going to take a look at the graphs of the sine and cosine functions. So from the previous section, we learned that trigonometric functions are periodic. That is, their values repeat in a regular manner. The graphs of the trigonometric functions should provide a picture of this periodic behavior. So in this section, we're going to learn how to graph sine, cosine, and tangent functions as well as their transformations. So now if we look at figure 6.18, it says coordinates of the terminal point of arc T give the values of cosine of t and sine of t. We know that from the previous section, that the coordinates of this point here would be equal to cosine of t for the x-coordinate and sine of t for the y-coordinate. Now, let's suppose that this arc is 2.53 radians, and we want to see what the y-coordinate is. So all we would have to do is sine. So if we go sine of 2.53, we're going to get 0.5741. Now, because sine and cosine are periodic functions, what would happen if we do sine of 2.53 plus 2 pi? Notice that we get exactly the same result. What happens if we do the same thing? So sine of 2.53 plus 4 pi. We get the same result. Now the reason is, as you know, is that the sine function as well as the cosine function have a period of 2 pi, because 2 pi is, in radians, a full revolution around a circle. The convention is to use the letter x to denote the variable in the domain of the function. So from here on, we will use the letter x rather than t and write the trigonometric functions as y equals sine of x, y equals cosine of x, and y equals tangent of x. Aside from their periodic behavior, these graphs reveal further properties of the functions for sine and cosine. First of all, notice that the sine function has a maximum value of y equals 1 for all x equal to pi halves plus a multiple of 2 pi, where in this case k is an integer, right? And you can see that the minimum value for the sine function is y equals -1, and this occurs for every x that is equal to minus pi halves plus a multiple of 2 pi. Now, if you look at the cosine function, you are going to see that cosine has also a maximum where y equals 1, but for all values of x such that x is equal to k times 2 pi for any k belonging to the integers. And you will see that the minimum for cosine is going to be y equals -1 for every x such that x equals pi plus a multiple of 2 pi. Now this confirms that both functions have a range between -1 and 1. And also, obviously, the domain for both functions is all real numbers. A little bit of a closer inspection to the graph of the sine function is also going to reveal that it is odd. That is, it has symmetry with respect to the origin. Notice that sine of minus x is equal to minus sine of x. So sine is odd, whereas the cosine function is even. That is, you can see a reflection across the y-axis. In other words, cosine of x is equal to cosine of minus x. Next, we're going to talk about the graphs of transformations of the sine and cosine functions. In section 1.5, we learned how to transform the graph of a function by horizontal and vertical translations, by reflections in the coordinate axes, and by stretching and shrinking, both horizontally and vertically. So this is a review of transformations of graphs of functions. We assume that a, b, c, and d are real numbers. So to obtain the graph of y equals f of x plus d, we translate d units up when d is greater than 0 and d units down when d is negative. If we have y equals f of x plus c, we translate c units to the left when c is positive and c units to the right when c is less than 0. If we have y equals minus f of x, this is a reflection across the x-axis. If we have y equals a times f of x, this is a vertical stretch if a is greater than 1, or a shrink if a is a value between 0 and 1. Y is equal to f of minus x. This is a reflection across the y-axis. And if we have y is equal to f of b times x, this would be a horizontal stretch for values of b that are between 0 and 1, or a shrink if b is greater than 1 for a factor of 1 over b. So in this section, we are going to look at the composition of sine and cosine functions of the form f of x equals a times sine of b times x plus c plus d, and the same for cosine. Now, you will learn that a is going to affect something called the amplitude. B is going to affect the period. C is going to cause something called a phase shift. And D is going to cause a vertical shift. Let's continue with example 5.7. And it says, sketch the graph of each function on the interval minus pi to 3 pi. Letter A, f of x equals 2 times cosine of x. So remember that this 2 that is multiplying cosine is going to affect the amplitude. Normally cosine has an amplitude of 1 because it goes from -1 to 1 as the range. So we should have the same cosine function but stretched by a factor of 2 in the vertical sense. So let's take a look at that graph. So notice that the function in blue is y equals 2 times cosine of x, and the only thing that has been affected is the amplitude. So instead of going through 1 at x equals 0, it's going to go through 2. And all the other aspects of the function remain the same. Notice that it intersects the x-axis at the same points. But it is stretched by a factor of 2. For b, it says g of x is equal to cosine of x plus 3. So this is a vertical shift upwards by 3. We can see that in the graph. Notice that we have exactly the same cosine function, but shifted up 3 units. Normally, the function has a symmetry with respect to y equals 0, right, or the x-axis, but for cosine of x plus 3, that's shifted 3 units up to y equals 3. Other than that, everything else remains the same. For c, it says h of x is equal to 2 cosine of x plus 3. So this is both transformations simultaneously. So we're going to have that vertical shift upward, but also a stretch by a factor of 2. So notice that y equals 2 times cosine of x plus 3 is shifted vertically 3 units up, as we can see by the axis of symmetry, and also stretched by a factor of 2. 3 plus 2 is 5. You can see that going through 5 here, and it's those two transformations simultaneously. For D, we have p of x equals 1/2 sine of x minus 2. So that means that the sine function is going to have an amplitude of 1/2, and it's going to be shifted down 2 units. So notice here in blue, y is equal to 1/2 sine of x minus 2. You have the sine function with an amplitude of 1/2 instead of the normal 1, and shifted down 2 units because of the minus 2. So we continue with example 5.8, and it says, waves are produced in a long tank of water. The depth of the water, d meters, at t seconds at a fixed location in the tank is modeled by the function d of t equals m times cosine of pi halves times t plus k, where m and k are positive constants. The figure shows a graph of d of t for a time between 0 and 12, indicating that the point 2, 5.1 is a minimum and the point 8, 9.7 is a maximum. Part A, find the value of k and the value of m. So k, remember, is the vertical shift upward. Normally, these graphs for sine or cosine functions would have an axis of symmetry at y equals 0, or the t-axis in this case. Now, this axis of symmetry has to be somewhere here, right? It has to be somewhere between the maximum and the minimum. So the line y equals k has to be somewhere there. So how can we find k? Well, k is going to be the midpoint between the minimum and the maximum. So all we have to do is add them and divide them by 2. So we'd say k is equal to 5.1 plus 9.7 divided by 2, and this is going to give us 7.4. So that's k. This equals 7.4. And then m, as we know from here, is the amplitude. So what is the amplitude? Well, the amplitude is going to be half of the difference between those 2 points. So maximum minus minimum divided by 2. So m is going to be 9.7 minus 5.1 divided by 2. And that is going to give us 2.3. Sometimes m, not the amplitude itself, because the amplitude is always going to be the absolute value of the number that multiplies the function, but sometimes it can be negative, and that's going to imply a shift across the x-axis, or at least across the direction of the x-axis. But in this case, they told us that these are positive constants. For part B, it says after t equals 0, find the first time when the depth of the water is 9.7 meters. So this is very easy to find, because notice that the first time the depth of the water is 9.7 meters has to be here. And then we know that the second time is over here for 8. So that means that there's a period of 4 for this function. So that means that after 4 seconds, we would have had the depth at 9.7 meters. So the answer is going to be, for part B, t equals 4. So we're going to take a look at period and horizontal translation or phase shift of the sine and cosine functions. Given that b is a positive real number for both the sine and cosine functions, where we have a times sine of, notice that this is b times parenthesis x plus c plus d, and the same for cosine. They have a period of 2 pi divided by b. So b affects the period. In other words, the period for sine or cosine is going to equal 2 pi divided by whatever b is. And then you also have a horizontal translation or phase shift of minus c. That's when c has a plus in front of it. So a horizontal translation of a sine or cosine function is often referred to as phase shift. So the equations y equals sine of x plus pi thirds and y equals sine of 2 times x plus pi thirds both have a phase shift of minus pi thirds. We continue with example 5.9, and it says sketch the function f of x is equal to sine of 2x plus 2 pi thirds. So the first thing we need to do is to rearrange this function and be able to identify a, b, c, and d. So let's write it as f of x is equal to sine of 2 times x plus pi thirds. And then here we can identify a as being equal to 1. b is equal to 2. c is equal to pi thirds. And d is equal to 0. So there's no vertical shift. So we have the amplitude remaining the same, an amplitude of 1, but the 2 from b is going to affect the period. Remember that the period of the sine function is equal to 2 pi divided by b. b in this case is 2, so we're going to end up with a period of pi. And then c is the horizontal shift or phase shift, and it's going to be pi thirds to the left. So now let's go and take a look at the graph. So here, first of all, we have the normal function for sine, y equals sine of x. And in the second graph, we have y equals sine of 2x. So this is including the value for b. And notice that the period has now been changed to pi instead of 2 pi, right? So the blue line is, notice here that this is now going to be less than 2 pi as a period, but actually half. So notice that for the blue line, if we start from here, from 0, the period is pi. Whereas for the normal sine function, it starts here, but then it has a full period at 2 pi. So that means a horizontal squeeze, right? Now, let's take a look at the phase shift. So y equals sine of 2 times x plus pi thirds implies that we also have a horizontal shift or phase shift of pi thirds to the left. So notice that all we did was shifted pi thirds to the left. So instead of going through pi here at this point, we've shifted pi thirds to the left everywhere. We continue with example 5.10. And it says, here is a graph of a function in the form y equals a times cosine of bx. Letter A, find the value of a, and B, find the value of b. So recall that a, in this case, is just the amplitude of the function. And this is a cosine function, which normally has an amplitude of 1. We can obviously see that this one has an amplitude of 14. You can see that here and here. So a equals 14. Now the case for b is a little bit more complicated because b affects the period. Remember that the period for the cosine function is going to be 2 pi divided by b. So this implies that b is equal to 2 pi over the period. So if we look at the graph, notice that we start here, and when you reach the same point again, that is one full period. So that indicates that this function has a period of pi fourths. So that means that b is equal to 2 pi divided by pi fourths, and this is equal to 8. So next we're going to take a look at the graph of the tangent function. From work done earlier in this chapter, we expect that the behavior of the tangent function will be different from that of the sine and cosine functions. In section 6.2, we concluded that the function f of x equals tangent of x has a domain of all real numbers such that x cannot equal pi halves plus multiples of pi. This is for any k belonging to the integers. Also, we can see from the graph that the range of tangent of x is all real numbers. So with this, we could speculate that the period of tangent is pi. Now this makes sense because if you take the identity tangent of x is equal to sine of x over cosine of x, it turns out that whenever cosine of x equals 0, this function will be undefined. And that occurs for values of x that differ by pi. So as x approaches the values where cosine of x equals 0, the value of tangent of x will become very large, either very large negative or very large positive. You can see that here. Notice that as x approaches pi halves from the left, it becomes very large positively, and as it approaches pi halves from the right, it becomes very large negatively. So that means that tangent of x has vertical asymptotes as x equals pi halves plus multiples of pi. Consequently, the graphical behavior of the tangent function will not be a wave pattern such as the one that we saw was produced by the sine and cosine functions, but rather a series of separate curves that repeat every pi units. The graph gives clear confirmation that the period of the tangent function is pi. Also, we can see that y equals tangent of x has rotational symmetry about the origin. That is, tangent is an odd function, and therefore tangent of minus x is equal to minus tangent of x. Finally, we have example 5.11, which will be the last one on this video. And it says, sketch each function. Letter A, f of x is equal to tangent of 2x. So remember that whenever you have a number multiplying x, this is going to affect the period. And the period will equal, in this case for tangent, pi divided by b. So pi halves. So all we have to do is adjust the period for tangent. And instead of having a period of pi, we are going to have a period of pi halves. Also notice the tangent of 2x is equal to sine of 2x over cosine of 2x. So this function is going to become undefined where cosine of 2x is equal to 0. So notice that this affects everything because where is cosine equal to 0? That's going to be every pi halves, right? So cosine of 2x is equal to 0. This occurs where this is equal to pi halves. So that means that it's going to be undefined for x equals pi fourths and every pi half period after that. So let's take a look at the graph. So notice that the first asymptote after 0 is pi fourths. You see that? And then every pi halves, you have a repetition of the asymptotes because the new period is pi halves. And this happens in both directions. It happens in the negative direction and in the positive direction as well. So now let's take a look at B. B says g of x is equal to tangent of 2 times x minus pi fourths. So here we have two things affected, the period, and there's also a phase shift. So notice that the period here is going to be the same as in A. We're going to get a period of pi halves. So we have the same period as in A, like I just said. But we have to take into account the phase shift. So notice that we have a phase shift of pi fourths to the right. So that means that the asymptotes are going to shift pi fourths to the right. So if we had an asymptote, as in the previous case, we had an asymptote in pi fourths, the asymptote is going to be at pi halves, and then every pi halves after that, either to the right or to the left. So let's take a look at the graph. So notice that the period is the same as in A, but the asymptote, like I said, is going to be at pi halves, and then it repeats every pi halves in either direction.